Cool, we're good to go.
Great. Hello, my name is Max, and this is Glyph. We're going to be discussing epidemic broadcast trees, which is a replication strategy that Scuttlebutt, the protocol, uses. I'm calling in from Wellington in New Zealand. I think that's all I want to say as introduction. What about you, Glyph?
Cool, yeah, I am calling in from the Crags in South Africa. And been diving into SSB-EBT recently, something which was always a bit of a mystery to me, despite numerous attempts to try and unravel. So we're just going to chat about it today, in hopes of shedding some light on the subject for others who might be interested in, and potential implementers as well. So maybe let's hop over to the diagrams now. We can talk a little bit about create history stream, kind of classic replication strategy of Scuttlebutt, and then contrast that with T.
Cool.
Great, do you hear me all right over mumble?
Perfect.
Excellent. Yeah, so most clients, Scuttlebutt clients, initially used a replication protocol using a MUX RPC request called create history stream. So this is where you send a request to a peer, specify a feed that you're interested in, and the latest sequence number you have for that feed. And if the recipient peer has more up-to-date messages for that feed, they would send those back. This works very well. It's quite a simple replication strategy. But the problem comes when the social graph grows and you may be interested in many feeds and you may be connecting to many peers. You need to send a separate create history stream request for each and every feed you're interested in. And if you connected to 3 or 5 or 15 different peers, you would request those same feeds from all of them. So the network overhead really grows quite large, quite quickly.
And there's quite a lot of redundant communication, right? Because and it's just super heavy because you're going, what about Alice? What about Bob? What about Carol? What about Dave? What about Eric? Whatever, in a big loop.
Exactly. Yeah, so it is effective, but it has these drawbacks. So I think somewhere along the line, Dominic was thinking about a more efficient replication protocol, and he had started designing something, is my understanding, and then he came across an academic paper titled Epidemic Broadcast Trees. And that is, fortunately, I always forget their names, but three Portuguese researchers. That paper was published in 2007. And
I think it was called Plum Tree or something like that.
yeah, so the protocol they define in that paper is called Plumtree, which stands for lazy push multicast tree. But the paper itself was called Epidemic Broadcast Trees.
Got it.
And
I remember him also at the time. I remember him also at the time talking about how where it was going for was this sort of like sweet spot where, like, how do you get messages across a network graph where the topology may be changing. The most naive approach is like a flooding approach where you just like spam everything at everyone, and that's kind of a little bit what Create History Stream was doing, was like playing everything from everyone. Um, Whereas Epidemic Broadcast Trees is like that, but like slightly smarter. Like it doesn't ask everyone everything. But anyway, you go on, please. You know a lot more detail.
yeah, so before we dive into SSB-EBT, I'll just add a little bit on that same point of this Epidemic Broadcast Trees paper and Plumtree, is that part of my confusion previously was that I thought SSB-EBT and Plumtree were a lot closer in the protocols, but actually they're quite different. So once I realized that, it almost became easier because I was looking at these Plumtree implementations and then I was looking at the SSB-EBT JavaScript implementation, and I was like, wow, these things are really quite different. So what Plumtree tries to do is have this balance, like you were speaking about, between epidemic broadcast and a deterministic spanning tree.
Right.
Yeah, so let's dive into SSB-EBT, and we can always circle back to some of those similarities and differences at a later stage. So we'll start off with an EBT session. So understanding how is the replication session initiated. So first of all,
Can I
go
can
ahead.
I throw, in terms of like I quite like brief hand wavy description followed by like session level detail. Can I do that? Can I have a go at that?
Absolutely.
So my understanding of epidemic broadcast trees is it's a little bit like the real world situation where, like, when I catch up with you, it's not like a completely blank slate when I bump into you online or on this call, for example. I have some memory of what we've talked about in the past, so I kind of know. Last time we talked about something that Stoltz had been up to, and so I already have in my memory some placeholder about where you're up to, and so if you combine a little bit of memory about other people's state and your state, then you can vastly reduce some of the redundant communication.
That's 100% correct. Yeah, in the context of EBT in Scuttlebutt, that facilitates request skipping, where you have persisted the state of the peer that you've connected to, and you know which feeds they were interested in previously and up to which point. So if you hadn't learned anything new about those feeds, then you wouldn't share it. It would be a bit strange in a social interaction if you kind of just started regurgitating everything you knew about every friend you had in common. But yeah, like you're saying,
Mm-hmm.
in this case, you are remembering some prior interaction and sort of where you got to in the conversation, and you can pick up from there.
Yeah, cool.
Nice. Yeah, so let's jump into the session. So, of course, before we can replicate, we need a network connection. And in Scuttlebutt, we use TCP connections. So let me zoom in a little further. So for the sake of this discussion, we're going to use the classic Alice and Bob names for our peers. So before replication begins, Alice initiates a TCP connection with Bob. The connection is successful. They do a secret handshake and set up their box streams so that they have this encrypted communications channel. At that point, they're ready to start sending MUX RPC requests. So this is the point in the diagram where we've got this green box that says network connection is now established. So because Alice was the one to initiate the TCP connection, she takes on the role as the requester in the EBT session. This is quite an important point. There are two distinct roles, the requester and the responder. So she will send an EBT replicate request to Bob, which signals that she wants to engage in an EBT session. Bob receives that, validates the arguments of that request. If they're all good, he sends his vector clock, and we'll talk about more what that looks like. That is also sometimes known as a control message. Alice receives Bob's vector clock and she sends her own vector clock back. So this is the state that we were talking about previously. And then they are free to exchange messages. So this this whole thing is known as a single EBT session, and it can be quite long-lived. So at any point after the initial exchange of vector clocks, let's say Alice has received messages from a third peer that she's connected to, and those are for feeds that Bob might be interested in. Alice can then send an updated vector clock to Bob, and he can do the same. So it's a sort of continuous process back and forth.
So it's not the case that Alice would just send additional messages down the wire to Bob. She would send an updated vector clock, and then Bob would say, yes, please.
So it's the former in that if she already knows from a previous vector clock from Bob that he's interested in a particular feed, if she receives new messages that she knows Bob is interested in, then she will just send those messages on straight. So that's a kind of push replicate approach. But she may be learning about new feeds, for example, where she's not sure if Bob is interested. So then she could send a vector clock, and then Bob might respond with his own vector clock to signal, yeah, one of those feeds you included in your latest one, I'm actually interested in that now too. Please send messages if you have above a certain number.
I see. So I've got a question about that. It probably doesn't matter too much, but that means Alice would be revealing the existence of feeds which Bob may not have otherwise discovered. Is that correct?
That's correct.
Huh, that's interesting.
Yeah, so maybe let's look at what those requests look like a little bit, and we can look at what a vector clock looks like. But I'll just say in terms of the Plumtree protocol, for example, in Plumtree there's this concept of eager peers and lazy peers. And eager peers just send messages to. When you learn about new messages, you send them. Lazy peers, you would just send the message identifiers or the hash of the message. And then those lazy peers would explicitly say, oh, actually, I'm interested in that. So SSB-EBT is doing a similar thing in a way, whereby we have this eager kind of push-based replication, which is the exchange of the messages. But then we also have the vector clocks, which are these control messages, which are specifying feeds and sequence numbers, and that takes up sort of less overhead over the network. And the other peer can explicitly state in their own vector clock, oh, okay, actually I'm interested in that feed instead, please send those messages.
So is the lazy communication done with further vector clocks?
Exactly, yeah.
Nice.
Also,
Yeah, so do you want to tell us about some of those requests, like those messages, those blue and yellow?
yeah, let's do that. So the blue and yellow follows the same pattern as Alice and Bob. So here is just zooming in. So here's the EBT replicate that request that Alice sends. It's a stream type RPC request with a JSON body, and it's also a type duplex. These are all important things in an implementation, otherwise another peer will not talk back to you. And there is this arguments feed which has a value of an array with a single object, version 3 and format classic. So when Bob receives this request, he's going to check that all these flags and fields are correct, and specifically that the version is 3 and the format is classic. If that is not the case, Bob will send back a MuxRPC error response.
Is that format classic the feed format?
I believe so, yes.
Cool.
yeah, I think maybe with some of the meta feeds work, this allows the possibility of specifying feed formats.
Great.
So then, assuming everything was valid, Bob sends his vector clock. SSB style, because this is a stream, we've got the request number is just the negative of the initial request number. And we have this JSON object with fields and keys and values. The key is the @prefixed public key of a scuttlebutt peer, identifying a feed. And then the value is an encoded value. So at first glance, you might think, oh, this is a sequence number, but it's a little bit more involved in than that. And we'll go on to describe the encoding and decoding. But in a nutshell, this is what a vector clock looks like. We'll go into this in more detail, but the -1 here means that Bob is not interested in this hecky feed. He doesn't want to receive messages and he doesn't want to send them.
Makes sense, yeah.
And both peers, when they receive the vector clock, they're also going to be sort of validating it to ensure maybe there is a feed included where the public key is malformed in some way, or maybe the value field is a string instead of a JSON number. That would also terminate the session with response. So we see Alice's vector clock as well, and there is some overlap here in feeds, so they some potential for messages to be sent back and forth here. And then when messages are sent, so the value of a scuttlebutt message is sent, this is exactly the same as would be sent during create history stream, the request type with message contents. Yeah, so that part's all pretty straightforward. It's the encoding of the sequence number, which is quite interesting. Take a look at it now. So let's say we start with an encoded value. I have this table down here with some different values, -1, 0, 1, 2, 3, 12, and 450. So we are going to check a couple of things as we decode this number. So to begin with, we have the sign of the number. Is it negative or is it positive? That specifies the replicate flag. So as I mentioned previously, if the number is negative, the peer who sent that in their vector clock is signaling, look, I'm not interested in this feed. I don't have messages to give you, or I don't want to give you messages for this feed, and I don't want to receive any. So in the table, we see that the replicate flag is false, and the receive flag and the sequence number are therefore irrelevant. If it's a positive number, that straight away signals that the peer who sent the vector clock wishes to replicate this particular feed. So if we had received this encoded value, we're now going to decode it and pass the JSON number as a signed integer. We then read the least significant bit of the binary representation of the number. So that's going to be the very rightmost bit, which of course will either be a 0 or a 1, and that encodes the receive flag. So if it's a 0, this means that the peer wishes to receive updated messages for the feed. So not only are they willing to replicate in an outbound manner, also want to replicate in an inbound manner. If that bit is a 1, it means they do not wish to receive updated messages for that feed. And then finally, we drop that bit, the least significant bit, and you can do that by performing an arithmetic right shift. And then the resulting number is the sequence number. So this specifies the sequence number of the latest message the peer has for that particular feed. And
Nice.
yeah, it's quite elegant, and thankfully I should mention Barak, who created some EBT documentation as part of the planetary team, and it was Barak's description of this encoding and decoding that was a big aha moment for me. So yeah, big thanks to Barak, because otherwise I might still be in the dark regarding this. And yeah, if you want to encode a sequence number, of course you can just do the reverse. You perform an arithmetic left shift, set the receive flag, and then set the sign of the value.
Right, and so that table that you've got down there below is an example of working through a range of different numbers for people who want to get an idea of it, right?
Exactly. Yeah, so we sort of see the pattern that odd numbers have a replicate flag of true and a receive flag of false. Numbers have both true. And then the sequence number itself ends up looking quite different to the encoded value. So that's why I sort of mentioned that one could be confused at first and think that the encoded value is simply a sequence number. That's not the case.
So one thing that became apparent listening to you describe that, which I hadn't known before, was that the replicate and the receive flag, replicate is kind of like I'm up for replicating outwards, and receive is like I'm up for replicating inwards, like I would like to receive. Is that correct?
Exactly.
I never was sure. Okay, yeah. Interesting naming. Yeah, naming is hard, of course, but that's really helpful clarification.
Yeah, and I've definitely had some confusion about this. I noticed in my implementation, for example, that I had a code comment which actually had this backwards. So yeah, I've thought about this scenario, for example, if you were following a feed and then you unfollowed, maybe you have messages for that feed that you're happy to pass onwards, but you're not really interested in new updates. So that would be a case where you'd want the replicate flag to be true, but the receive flag to be false.
I had another question. Uh, it's not it's going back to the lazy and eager thing. Should I hold that question, or is now a good time?
Let's quickly go over request skipping and vector partitioning and fallback mechanisms, and then
Okay, yeah, great.
and then we can chat about some more comparison of eager and lazy. Yeah, so I don't have diagrams for this next part, but we can just, it's easy enough to describe. So we already spoke a little bit about request skipping, whereby in a session with Alice and Bob, Alice is going to store the vector clock that she has received from Bob. She's initially going to store that in memory, and she might persist that to disk to allow retrieval between the application lifecycle. And then before sending her vector clock to Bob on in a subsequent replication session, she's first going to check the stored vector clock and just populate a new vector clock based on the difference of like, okay, Bob sent XYZ feeds with these sequence numbers in his previous vector clock. Let me check my local database and see if I have any updates for those feeds. So that's request skipping, which helps to keep the overhead low. You can keep the total vector clock size down. Otherwise, you'd just be repeating yourself quite a lot. So that's quite a clever.
It's still quite nice though, but it's like you don't have to implement that initially. Like that's kind of like a value add, but you can still use verbose vector clocks to start with if you need to, right?
Exactly. Yeah, that's one of the really nice things about implementing this is the core is quite straightforward, and then there is layer upon layer of optimizations that one could implement. But you totally wouldn't have to have successful replication. You'd just be maybe a bit of a a chatty neighbor or just a bit of a context unaware neighbor. So that's request skipping. And then there's something which I don't think it's called this in the implementation, the documentation, but I think of it as vector clock partitioning. So I believe in set theory, partitioning is the correct term, where you have a set and you're going to split the elements of that set into multiple groups with no overlap, so that the total set is represented throughout those subgroups, but exclusively. So let's imagine that Alice is interested in 100 different feeds and she has 10 peer connections. So she's going to engage in 10 EBT sessions with these 10 different peers. The sort of naive approach is to send a vector clock with all 100 feeds to each of those 10 peers. And that's what you could do initially in your implementation. If you use partitioning, you would send each peer a vector clock with just 10 feeds. So you'd split the 100 feeds you're interested in into 10 different groups and just ask each peer for that subset of 10. So this means there's no overlap, so it can be very efficient. What can happen then, though, is maybe I ask for 10 particular feeds from Charlie. Charlie doesn't actually have any of those feeds, but Daniel does. So I could use a timer which starts when I initially send the vector clock to Charlie. And if I don't receive any messages from Charlie for those feeds within that time limit, I switch those feeds to another peer. So maybe I would say, okay, ask Charlie. Charlie isn't giving me anything. Let's try Daniel. So yeah.
Right. So would that look like I send a vector clock update to Charlie saying I'm no longer interested in Omicron or whatever in some feed, and then you send a vector clock to Daniel saying I'm now interested in Omicron.
Exactly. Yeah. You could do that. You could also get away with not updating Charlie, for example, because we could take Charlie's silence as saying, well, actually, I don't have anything for this, and just pass it on to Daniel. Or the better thing to do would be what you described.
Nice.
And then you could even add another layer on top of this. You could keep track of, okay, which of my peers generally have messages earliest for which feeds. But then it really does get quite complex. But especially if you were trying to prioritize low latency, this is something that Plumtree does very well. You do that kind of level of optimization.
And I think that from like memory of conversations with Dominic, you kind of want memory, but you don't want hard memory because the network topology may change, right? Like if one of my friends is currently living in Berlin for the winter because it's warmer there, they may be the best person to talk to for updates from other friends in Berlin, but when they like move back to Sweden in the summer, they may no longer be like, you know, the network topology changes, and so you need to be able to like have you need to be able to adapt your memory, not just like get stuck with a particular memory that you should always ask this person because they've, you know, have historically been super reliable.
Exactly. Yeah, so if you have that kind of deterministic tree, you have a sort of one pathway. It can be great for latency if you're optimizing for the shortest connections or shortest response times. But as you point out, if one of those nodes in the tree drops off, now you've got this fault, you've got this break. So you have to be able to heal that. So that's where not having such a holding so tightly to your memory, as that metaphor is a good practice. And Plumtree gets around this with the eager peers form that deterministic tree, and then the lazy peers allow one to fill in the gaps. And I guess we could chat about this briefly now, is that SSB-EBT is a bit different because the needs of the network and the underlying protocol are different. So Scuttlebutt really emphasizes eventual consistency. So if we go back to that epidemic broadcast protocol we mentioned right at the beginning, so let's say my node starts up, I know about 10 different peers, I pick 5 of them at random, and I broadcast all my messages. Each one of those peers picks 5 nodes that they know about and they broadcast. This is great for scalability and for low latency, but you have a lot of redundancy, and you also have the problem whereby maybe my node comes online after that ripple has moved through the system of those particular messages, and now I may never receive those messages, like I'm late to the party.
Mm-hmm.
And Scuttlebutt, we have the situation where someone may not start their Scuttlebutt client for a year, and when they do start it, they still want to learn about all those feeds they were interested in. So this sort of explains some of the difference in the protocols. We have these append-only logs, and we really want eventual consistency. So being able to query for particular logs and sequence numbers is really important.
Yeah, nice.
And
so one thing that crossed my mind that we didn't say earlier is that all of this works because a feed is like a linear linked list in Scuttlebutt, where you've got where the sequence number is how far into the linked list you are.
exactly, yeah, and the sequence number can only increase, and it's like a monotomically increasing sequence.
Mm-hmm.
Yeah, so then the last thing I wanted to bring up was just to chat briefly about fallback mechanisms. So not every Scuttlebutt client implements SSB-EBT replication. There are some clients which may still only use create history stream. So how do we detect these cases, and how do we fall back? And one could come up with quite a few scenarios, but let's talk about 3. And I should mention here that this is now documented in the Scuttlebutt protocol guide, so if anyone wants to look at that in more detail, they can check that out. So the first scenario, let's say Alice connects to Bob, and straight away Bob sends a create history stream request. This is a good sign that Bob doesn't implement EBT, and so we fall back to using create history stream. Classic replication. Second scenario would be Alice connects to Bob, Alice sends an EBT replicate request, and Bob returns an error response. Then that's also a good sign. Okay, well, let's fall back to classic replication. And now I'm trying to... you could also use a timeout. So Alice sends the EBT replicate request. Within a certain time, she doesn't hear any Bob. She can fall back to create history stream.
That makes sense.
Yeah, so that's a nice way to still be able to support both.
For what it's worth, I was saying to Glyph before this call started that so I maintain and build a client called Aho, which doesn't use EBT yet, even though EBT's been around for like 5 or 6 years. However, there are some gnarly bits in this code, and at least in the JavaScript implementation, and one of the edge cases that I'm like scared of is that I think in the JavaScript implementation, and this may have been fixed, but if the memory is slightly wrong, like if you have an out by one memory recorded, or you don't, if the memory, I think the memory might be too strong or like slightly faulty in a couple of cases, and I've been daydreaming about what would it be like for memories to be randomly dropped, because I'm scared of it getting into a locked state where it's like something gets recorded slightly wrong, and because of that you just never get updates or something like that. I don't know if that seems possible, but I'd have to think about that more given what you've told me, or like what I've learned here.
I see what you're saying. Yeah, so maybe were if you had the stored sequence number of one ahead of what you actually had, you may be ahead of your peers. I think it would resolve itself eventually because they would, if they got sufficiently ahead, let's say you had stored, I have up to sequence number 40, they got to 45, then send the difference. But yeah, I think that's something certainly that there should be tests for.
Okay.
But also my ability to read JavaScript code, particularly, shall we say, the more esoteric forms of JavaScript code, is not great. So I'm far from an expert on the SSB-EBT code base. But yeah, let me maybe just quickly point to a couple places that folks can go if they want to look deeper. So, of course, there is the Scuttlebutt protocol guide, which now has an EBT replication section, which kind of talks through in a bit more detail everything that we've chatted about today. Then, if you're interested in a JavaScript implementation, there are two libraries. First, there's Epidemic Broadcast Trees, which is meant to be a sort of generic implementation. And then there's SSB-EBT on top of that. There is also in ScuttleGo, which is a Go implementation of Scuttlebutt. There's an EBT implementation. And a Rust client I've been working on called Solar also has an EBT implementation in the works. It's not pushed yet. There are a few more additions to make, but yeah, there are now more implementations than ever to have a look at. And I know Jeremy List has also been working on SSB-EBT implementation. I believe it's C++.
Is he the one building the Haiku client?
That's right. It's called Habitat.
Nice.
Yeah, any more questions or things you want to discuss before we wrap up?
Oh, so apologies if you already covered it. How do you transition? So is it my role to decide who gets which of my connections I want to promote and demote to eager, or like how do I lazy? How do I transition between eager and lazy, where I'm just saying, oh, just push me vector clock updates, please. Don't push me just messages.
So yeah, this is one of the differences between Plumtree and SSB-EBT. SSB-EBT doesn't have some explicit differentiation between eager and lazy. All of that kind of information will just be encoded in the vector clock.
Yeah, but in eager mode, like sorry, if if I'm Alice and I'm talking to Bob and I have an eager connection with them, I guess. This is a few questions. One of them would be like, would it be eager for all messages that would come from Bob, or would it be eager just for messages about Carol, but lazy about other ones? So that's one question. And then a second question would be, how is it that a connection between Alice and Bob gets demoted to from eager down to lazy, or promoted from lazy back up to eager? Like, how do I know whether we're talking in vector clocks? So I think if you're sending vector clocks, that means you're in sort of lazy mode, kind of more, and eager mode is just you're pushing messages, right?
Sort of. Yeah, at the risk of confusing, I may have confused things by bringing in eager and lazy, but essentially,
Mm-mm.
so vector clocks will always be exchanged. That's the kind of prerequisite for any messages to be exchanged. So we could,
Yes, yes.
yeah, if I've explicitly specified a feed in my vector clock and said that I want to replicate it, and Bob has also specified that feed in his vector clock, then Bob knows, okay, glyph is interested in this feed up to this sequence number. I've got new updates. I'm going to send messages because I've already signaled in my vector clock that I'm interested. But maybe there
Right.
is a feed that I haven't included in my vector clock that Bob knows about. Bob's going to include that feed in his vector clock to signal like, oh, hey, you haven't mentioned this other feed, but I have it, and this is the sequence number I have up to, and I'm happy to send you the messages. So you could kind of think about that as a lazy mode signaling because the amount of data
Mm-hmm.
that's transmitted is quite small. And then I could see that feed listed in Bob's vector clock and for whatever reason decide, oh, actually now I'm interested in that feed too. Let me send a new vector clock where I express my interest in that feed, and then Bob is going to send messages.
I guess, is there any reason in the protocol why you couldn't, say we do our initial exchange, you and you say, look, I've got Stoltz up to 300, but I'm not interested in receiving more right now. And then I'm like, okay, cool. But then I like get a lot of updates from Stoltz, and like I'm now up to Stoltz 500. Could I send a vector clock saying, look, I've got Stoltz at 500 now, and you could go like, huh, okay, let's have a look. Sure. Um,
Yes, you could 100% do that because you are communicating some state change of the feeds you know about. And
mm-hmm,
you don't have to, well, it would sort of be bad behavior to send a new vector clock every time a feed you knew about changed, but you might bundle those changes. You may bundle
mm-hmm.
them according to the number of feeds that have changed or the amount of time that's passed. But yeah, there is this kind of ongoing communication of vector clocks back and forward to express these state changes.
What happens? Now I'm just poking for edge cases, but what happens if you say, I'm not interested in messages from Stoltz, thanks, but I can give you some if you want. And then I like send down the wire some messages about Stoltz. Is that considered bad behavior and gets you disconnected, or like what?
It's a good question. I think this would be an implementation detail because I don't know of any particular specification around this case. Would certainly be bad behavior. I may choose, like what I would do in an implementation is I would keep track of which feeds I'd requested. So if I
Mm-hmm.
received a message in response which belonged to a feed which I had not explicitly um, requested, then I would just ignore that message. I may take it a step further and decide, okay, if you send X number of messages that I didn't explicitly ask for, I'm going to terminate the session.
Mm-hmm. Yeah, it seems smart because like if you're trying to conserve bandwidth. Yeah, that's all the questions I have. That was really that wasn't as scary as I thought it was going to be. That's really accessible feeling.
Cool. Yeah, I'm glad to hear that. I definitely reached the same conclusion through my reading and research. yeah, as I said at the beginning, for many years, there were sort of several times when I approached this thinking, maybe now's the time to implement this. And I was sort of a bit too daunted. But once again, huge thanks to Barak, who was really the one who helped to demystify this for me.
Mm. I know. I know Stoltz has been doing some work on this potential successor protocol called PPPPP codename. And one of the things that he's talked about is that partial replication is one of the things that is of interest in that context, and it could be yeah. So doing range requests, for example, isn't something that this protocol currently supports. Like you can't say, I don't really care about the history. Can you just like give me the latest 100 from that you have from Stoltz or whatever? You can't really do that in this context. Have you talked to him at all about or heard anything about whether he's considering using EBT in that?
No, I have not had any such conversation.
Okay. Well, I might I may have a chat with him about that, and could be a good follow-up show and tell as well. Yeah. Is there anything else that you would like to close with, if we're reaching the end?
No, I don't think so. Just that I am happy to help anyone with follow-up questions. Of course, I am on Scuttlebutt, or I can also be reached by email, glyph@mycelial.technology. And yeah, thanks very much for
Awesome.
hosting the session and suggesting this in the first place. It was a lot of fun to come up with the diagrams, and it really helped me to think through things in more detail.
Yeah. Thank you so much for putting in all that work. It's really, yeah, these diagrams are great.
Great. Thanks, Mix. Take care.
Yeah. Bye.
Bye.